And welcome everyone to another HERC cyber seminar. And my name is Mark, and what I'll do is I'll talk about cost and how we model it as a dependent variable. And before I do that, I wanted to at least poll the audience, and I was hoping you can help me out with this, Maria, to see if, what kind of experience our audience has had when it comes to modeling cost data.
And that poll is now open, and the results are slowly coming in. So what types of models have you used for cost data as an outcome-dependent variable? Your choices are A, ordinary least squares linear regression model, B, log transform model, C, generalized linear model, D, two-part model, and E, I have never modeled cost as an outcome before. And the results have slowed down, so I am about to close that poll. And the results are 14% say A, 14% say B, 28% say C, 17% responded D, and 22% said E.
Well, thank you. It's a nice distribution of people who use cost as an outcome variable, and also those who have not used it before. And this is really nice to know, because what I'm going to do is really kind of go over some of the practical aspects of how at least I do it when it comes to modeling cost data, especially in a regression model. And hopefully some of the stuff we teach you today will be useful in your own practice. So with that being said, we've done these presentations before, and I would like to draw your attention to Dr. Paul Barnett's presentations in the past. And he's done an excellent job of discussing cost as a dependent variable from a theoretical perspective as to why we have some issues with this, and also some practical applications of the current tools that we use to address those issues. So for those of you who are interested in seeing a much longer discussion about this, he did a two-part series on it. I provided the links here for you. Now, just a little background. For those who are not familiar, cost is an unusual type of outcome in the sense that it's almost always skewed to the right with these thin tails. And these thin tails usually represent subjects or patients with generally high costs that tend to drive the mean. So it's always an issue whenever we try to model this, because technically when you use regression models like OLS, there's always this assumption that things are normal or normally distributed. And that's not always the case with cost. And in addition to that, there's also a substantial point mass of subjects that don't have any expenditures in healthcare, so they would have zero cost. And these tend to be a problem sometimes whenever you're trying to model cost, especially on a continuous distribution scale, because you have a lot of subjects with zero cost, and all of a sudden you have subjects with this weird sort of right skewed distribution. So these are some of the major issues when it comes to modeling cost data. And what I'm going to talk about today is how we can model it using OLS, as well as a variety of different models. But I wanted to show you how OLS, although sometimes sufficient, may cause some biased estimates. And we have to think about alternative models other than OLS in order to get some unbiased estimates of the average cost or the average healthcare expenditures in our data set. Now, some characteristics, quickly, I want to run through some characteristics of these data that we're looking at. Like, first of all, we look at skewness, and generally skewness, if it's normally distributed, we have a skewness of 0. And the kurtosis, which really measures how heavy the tails are at the ends of the distribution, we usually want a kurtosis around 3. Now, these are sort of characteristics of a normal distribution. However, when you look at cost data, you'll notice that the skewness is going to be very, very different from 0, and also the kurtosis will be very, very different from 3. And I try to put Stata code here. This is generally where I do a lot of my work. So for those of you who are interested in recreating some of these graphics and some of the results, I do have the Stata code available on GitHub, and I'll show you where you can get that later today. And another characteristic about data is this idea of homoscedasticity. And what we're looking for with these residuals is whether or not the residuals are sort of following some kind of pattern when it comes to some of the fitted values of sort of the independent variables. And what we want is something that's sort of this cloud of distribution where you really don't see any patterns of the residuals. Because when you do, you have some issues when it comes to the variance of the residuals. As you can see here, we see some kind of weird pattern where the residuals are sort of getting, the variance of the residuals are getting higher for increases, for higher values of the fitted mean. And in these situations, we tend to run into some issues when it comes to standard error calculations. And we can easily fix this by adding the robust, the Huber-White robust standard error estimator in our regression models. But I wanted to show that these are some of the characteristics we see when we're looking at residuals in any type of data set that we're looking at. And cost is no exception. We tend to see some heteroscedasticity with cost data, which tends to be problematic when you try to calculate standard errors. And for those of you in the audience, I made the data set that I'm going to use today publicly available. So if you want, you can actually download the data from MEPS. We're going to use the MEPS 2017 data set. And this is the medical expenditure panel survey that AHRQ sends out and curates. And we're going to look at the total healthcare expenditure as our primary outcome. I've also curated the data. So if you wanted to just download a very limited data set that's clean, I've uploaded that on GitHub. And if you click on this link, you should be able to see that the limited data set's here under a DTA file, which is a Stata-based file. You can download that onto your desktop. This is the link to the Stata code for all the exercises we're going to do today. So you can go ahead and click on this, and you can just copy and paste that into a brand new Stata do file. So you can follow along or do this on your own after the presentation is done today. A couple of housekeeping items I wanted to talk about. For those of you who are not familiar with Stata, whenever you download data, you have to always change the directory for where Stata is pointing, so that way you can use the data. So I've included some instructions on how to do this. It's very easy to do. If you're using Windows, for example, you can always use the File Explorer to copy and paste the pathway here into the command line here. Make sure you keep the quotations here. That's how Stata identifies the file path. It's a little bit different for Mac users. For Mac users, what I do is I tend to drag the folder into this area under the command line, and that generates the file path for the Mac OS. And just like Windows, you just copy the file path here into the quotations, and you should be able to use that data that you downloaded from GitHub. Okay, so hopefully that should be clear in terms of how you can upload the data into Stata from GitHub. Okay. I wanted to go over some goals I had for you today. Primarily what I wanted to do was just try to evaluate the average total healthcare expenditures among household respondents in the MEPS 2017 data set. And these are patients that are diagnosed with high blood pressure. So there's a diagnostic code in there that we use, and I've actually cleaned the data. So we were only focusing on patients that have high blood pressure. And pretty much what we're going to do today is just look at a lot of different regression methods to model cost and then see how these results are different. And we're going to control for a couple of baseline demographics, things like the subject's age, their gender, race and ethnicity, poverty status, marital status, and also census region. And there's a couple of notations. Usually I use Y to represent the dependent variable. In this case, the dependent variable is cost. I use X sub I to represent the array of different independent variables I'm going to control for in the model, like things like age, gender, ethnicity, and race. And then the beta sub I represent the regression coefficients from the model. Now the analytic plan, we're going to look at a couple of models. Ordinarily squared, this is more, this is your linear regression model. And we'll look at a log OLS model. We transform the cost data to make it look more normal. But there are limitations with this. So we're going to look at a sort of a correction factor called the smearing technique. And we're also going to compare these results to a generalized linear model. And then finally, we're going to look at the results of the two-part models and see how different these are when you start comparing them. I always like to do some type of goodness of fit test on all my models to kind of give me an idea of how well the model is fitting the current data. And then what we're going to do is just compare the means. And we're also going to compare things like standard deviations as well as the medians. And just to kind of give you a little background on some of the goodness of fit tests I use, I just want to let you know these are just guidelines to help you determine whether or not the model you have is a good model to represent all of your data. I wouldn't say these are definitive tests you can run, but they're just helpful in the sense that you can use these to help guide you in terms of selecting the correct test. So we'll use the Pearson correlation to model the raw scale costs and the residuals. That should actually be residuals, not predicted costs. So what we're looking for is whether or not there's a relationship or an association between the residuals and then the predicted costs. We're going to use the link test to see whether or not some of the predicted values are associated with the raw values. And this is a specification test to help us determine whether or not we have the right specification for our dependent variable or even our regression model. And the Hosmer-Lemmerschau test is a modified version of that. What we're going to do is we're going to plot the residuals across deciles of predicted values of the linear estimator. And we're going to do some kind of joint test to see the mean residuals are different from 0. And what we're looking for is, for all of these tests, whether or not they're non-significant. Because if they're non-significant, that means we have a pretty good model. But if there are significance in any one of these tests, then we need to really think hard about whether or not the model we have is actually the right model for our data set. So here is just summary data of our total expenditures. So if you were able to download that and follow along, you can run the summarize command just to look at some of the characteristics of the data. I have a histogram here, so you can see there's a lot of there's a huge point mass here at near 0, and you can see that this is right skewed. And it's very hard to see, but there are a couple of subjects with very high cost. We have a subject with about $550,000, $500,000, $499,000, and $474,000. We have some pretty, just a few subjects here that are just driving the mean this way. Now, when you think about some just simple descriptives, we have about nearly $10,600 in terms of the average cost with a standard deviation of $24,000. And we have a high of about $550,000 and a low of $0. As I mentioned before, for normal distribution, what we want is a skewness of 0 and a kurtosis of about 3. Here we have a skewness of about 8.6 and a kurtosis of 136. So clearly this is not normal. And I'll show you how we can model these using other models to try to make this look normal, so that way we can get some unbiased estimators. So the first model I'm going to run is the traditional ordinary least squared model, and this is the structural form of the model. So we're looking at the expected value of y, which is the cost, given some array of x. And this is your typical linear regression model that's designed in a linear form. And we have our x's here, and these are the covariates that we'll be controlling for in this model. Now, what I like about linear models is that they're pretty robust to a lot of violations of its initial assumptions, like violations of normality and things of that nature. As long as you have a large sample, it's pretty robust. And it's very easy to interpret beta coefficients because they're actually in just cost or raw data. So if you see any type of changes in the outcome due to some kind of change in the covariate, it's very easy to interpret. However, because of the high skewness and also the sensitivity of the mean to any type of outlier, it does generate some problems. With cost data, we don't want to trim the data because those outliers are very important for us because they represent real patients. So having a model that is not that sensitive to the skewness could be helpful. But unfortunately, OLS models are very sensitive to that. And of course, if you have nonlinearity of the y, you can get some unbiased estimators, and that's always a threat. But as I said before, OLS models are pretty robust to that. And of course, heteroscedasticity is always going to be an issue. This is something that happens when you have variances that increases with the mean. These could generate inefficient standard errors, but you can correct for that by adding some kind of Huber-White sandwich estimator to calculate your standard errors. So that shouldn't be too much of a problem with OLS models. Now this is the Stata code for that. You can find this in the GitHub page that I posted earlier, but I just wanted to show you what the heteroscedasticity looks like. You can see that there's a lot of distributions as you increase the fitted values. As you can see, this kind of mostly is in the positive quadrant, but you can see there are some values in the negative quadrant. And it does not look like anything that I showed you earlier in terms of what the homoscedasticity of the model should look like in terms of when it comes to the residuals fitted along the values. So we have some violation here, and that can be easily remedied by adding the robust estimator for the standard error. But with that being said, I wanted to add a second poll here. And Maria, if you can help me out here, I wanted to see how the audience can gauge whether or not the mean total will be similar or different between the OLS model and the raw data.
Okay, that poll is currently open. How different is the OLS regression mean total expenditure compared to the raw mean total expenditure? Your options are A, OLS regression mean is higher than the raw mean, B, OLS regression mean is lower than the raw mean, and C, both means are exactly the same. Also, to the audience, my apologies. We are getting the handouts corrected as we speak. Hopefully, we'll have that set before the end of the presentation. And if not, just check your email and you'll be able to see the links to everything. Okay, the responses are slowing down. I'm going to go ahead and close that poll. Hold on. And the results are, we have 18% that says A, 36% say B, and 36% say C. Back to you, Mark.
Great. Yeah, nice distribution there. So what I'm going to show you is going to surprise a lot of you. When we do the OLS model, we actually get exactly the same in terms of the mean, and this is just the design of the OLS. You actually get very good prediction on the mean when it comes just to calculating just the mean model. Where things get weird is the standard error, because you get things like negative values that shouldn't really exist, and of course standard deviation is underestimated compared to the raw model. So when it comes to OLS and the raw data, you technically will always get very similar, or if not identical values of the mean. But where the problem really lies is in the standard errors. And this is just a representation of that. So this is the predicted OLS model of the cost data. As you can see, it looks very, very normal, right? And as a result, we tend to get very close or even exact estimation of the mean. But unfortunately, of course, standard errors are going to be very, very off due to a lot of things like heteroscedasticity and then the skewness of the data. Let's look at some of the goodness of fit tests. This is interesting. Pearson correlation is non-significant, partly because the residuals are orthogonal to the predicted cost, and that's normal. We expected to see that. But the link test shows significance. And what that's saying is that the specification for the model, or even the dependent variable is incorrect, or there's something wrong with the OLS model. So that should raise a red flag that something's going on here. Now, the Hausman-Lemischel test, if you look at the residuals, if they're any different from zero, is non-significant. And this is not bad. And as I mentioned before, the OLS models aren't exactly always bad. They can be pretty robust, a lot of these things. And I've shown you how the residuals sort of zigzags around the central point of zero. And generally, when we look at these types of graphic, we're looking for is this zigzag pattern. And it just tells you that the model isn't really over-predicting or under-predicting the residuals according to the fitted values of the deciles. And that's a good thing. And that's what we're looking for here. And the OLS model, at least in this case, is showing that sort of zigzag pattern we're looking for. So visually, if you just want to look at this, and this is what I like to do, is to see whether or not we have this zigzag pattern where you're not really seeing too much of an overestimation or too much of an underestimation in terms of the residuals relative to the deciles of the predicted means. So this is not too bad. The link test does raise some red flags of whether or not this is a good specification for the model. So this is just a table to summarize the results. We have the raw results here. We see that the means are similar between the OLS and the raw data. However, the standard deviations are quite different. We see that the mean is bounded by zero and it goes into 500,000, which is nearly infinity. But here with the OLS model, we have a negative value, which is supposedly improbable. So this always raises a red flag whenever we calculate the mean and max for the OLS models. And the median for the OLS model is very similar to the mean as expected because of the normal distribution of the OLS model, but we don't have that here with the raw data. Now, what do we do? So in the past, when we had these issues, we would just transform the cost data so that way it acts normally, right? So the way we used to do this, and I think some people still do this, is just to log transform the cost data. So when you do this, and then you look at the distribution, the cost data in terms of the log form is very, very close to normal. And it makes sense that why not just run an OLS model on the log transform data? And that's what some people have done in the past. And I'll show you where some of that can actually lead to some problems. One of the challenges when you log transform cost data or any data that's skewed is really hard to interpret the mean, because as decision makers and stakeholders, when they see data like this, it's really hard to allocate resources based on the log cost of anything, right? So you have to retransform this, and this is where we run into a lot of problems with log transform models of the OLS type. The retransformation process, it tends to be a lot more difficult and challenging than the transformation initially to get it to look like it's normally distributed. So here's the log transform, the structure of the log transformed OLS model. And just keep in mind that the expectation of the log scale is not the same as the log of the expected values, right? So technically this is what we want, but when we transform the data, we're actually calculating the expected value of the log scale. And this is where the retransformation problems occur. For those of you that are interested in running this, I have the code here for Stata. And what you see is that we have a mean of about $3,900, which is very different from the raw mean of about $10,600. And again, we get a nice sort of closely normally distributed predictive data set with the log model. Let's look at some of the goodness of fit tests. We see that there's a significant correlation between the residuals and predicted costs, which is a big no-no. We see there's some kind of problem with the specification of the data. Despite transforming the data, there's still an issue with the OLS model for the log cost data. And when we look at the Hosmer and Lemeshow test, we see that it's significantly different from zero in terms of the mean residuals across the deciles. But more importantly, if you try to look at just the pattern of the residuals, you don't see that zigzag pattern that I alluded to earlier, meaning that this model is overestimating the residuals. So clearly there's a problem here with the log transform model of the OLS. And it's just a summary to kind of show you how different these values are from the raw data as well as OLS results. And all I'm trying to summarize here is that the log OLS model of the retransformed cost data is not a good one to use, especially in this case. But there are ways to sort of correct for this, and I'm going to talk about how you can use a smearing estimator to help fix this. So smearing estimator, basically, when you're thinking of the retransformation process, what you're really having an issue with is this retransformation of the expected value of the error term. And to correct for this, Duan created a whole algorithm in terms of how you can fix this. And what you're really trying to do is sort of separate out this error term here as you're calculating the smearing factor for it. And I've written the Stata code for this, but all you're really looking for is you're trying to exponentiate the transform cost from the predicted cost. And that can give you a factor that you can use to multiply with the expected predicted cost here. And when you do that, you're actually correcting for that sort of retransformation error. And you can get pretty close values to the raw cost. So here in this case, just to kind of go over some of the goodness of fit test, despite the smearing, we still get some issues with residuals being associated with predicted cost. We have some misspecification in the model here, and also we have some residuals that are still significantly different from zero across the deciles. But when you look at the zigzag pattern, you don't see that here. You see the sort of slight overprediction and then a lot of underprediction here with the residuals. And just to kind of summarize the results of the log OLS model with smearing, it's a lot closer now to the raw average cost, but it's still higher. The median is close to the mean in this particular case because it was normally distributed due to a transformation, but you can see that it's still not exactly the same, right? There are other ways to get the smearing factor to be more precise, but that will require you to sort of create a smearing factor for all of the different covariates. So for example, you can create a smearing factor for males, and you can create a smearing factor for female, and then sort of combine those two. But then you would also have to do it for all the different ages and the different regions and different comorbidities. So as you can imagine, this can be very, very intensive. But it is available in case you are gung-ho about using the log transform data. But what I'm going to show you next is probably a better single equation model, and this is the generalized linear model. This is something that I prefer to use whenever I do cost data. And what's really neat about this is that you're taking advantage of the link function here. And rather than transforming the raw cost data, we're transforming the expected value of the cost data. So in this case, the log of the mean is really just the linear form of the expected the linear predictor. So it makes it very easy to avoid the retransformation problem by using this sort of log link. I think of it as a cheat when it comes to these types of additive models, but it's very, very useful because you can actually add all kinds of different families and link to the model that allows it to be very, very flexible. And I have a table here for all the different types of family distributions you can use, as well as the different types of link that you can apply to the GLM model. And you can actually do you can get the same answer as an OLS if you use the Gaussian distribution with the identity link. That'll give you the same answer as a normal ordinary least square model. But what most papers will do is use the gamma distribution with the log link. This is a pretty good model for cost. You can try all these different ones to see which one gives you the best fit. But when we, at least when I write papers, I usually start off with this model, the gamma model, and then with the log link. And if it doesn't fit well, then I'll try to explore different types of model. But this is generally what I start with. And I'll show you how good this actually is when it comes to fitting the raw data in our data set. Now, since I showed you all these different families and these different links, there are ways to sort of empirically find out which one works the best, right? So as I mentioned before, I usually start off with the gamma model or the gamma distribution with a log link. But if you don't want to take that approach and you kind of want to do things empirically, there are ways to do that. So there's a test you can run that looks at this sort of, so you always look at the variance in relation to the expected value of the model. And this sort of gamma term here is what determines the sort of family that you can pick. So you can run a modified Park test to see whether or not the gamma should be 0, 1, 2, or 3. And of course, this is all empirically designed so that way it's based on the data you have. So if your cost data is very, very skewed or not as skewed, then this gamma would definitely be different. So for the most part, you can run the modified Park test to see which one of these best fits this particular variance distribution condition on your actual data set. And you can also run a link test that we did earlier to see which one is the sort of the best fit when it comes to the residuals, predicting the residuals, whether or not they're farly different from the deciles. But what I find with the link test is it's not as good or useful to run because a lot of times when I run this, they tend to be very similar. So I don't see too much distinctions here. And then of course, the modified Hosmer-Lemmerschau test is really nice because you can visually see how much of the residuals are over or under predicted. I just wanted to show you this, that way if you ever wanted to do a GLM model, you don't trust that the family is a gamma distribution with a log link, you can always empirically figure that out. Let's see some of these tests. All right, so now with the GLM model, as I said earlier, I usually start off with the gamma distribution with a log link. And running the model, you can see that the mean is very close to the raw data. So it's about $10,655. And just looking at the distribution, the predicted values of the cost, it's not necessarily normal, but it's kind of getting there. And we see that the skewness is 0.6 and the kurtosis is 3, right? As I mentioned earlier, for a normal distribution, the skewness is 0 and the kurtosis is 3. So we're very close to what we would normally see in an ideal normal distribution. And here we have the goodness of fit test. And as you can see here, we don't have any significant correlation between the residuals and the predicted cost, which is a good thing. And we also don't see any type of misspecification of the model because there's no association between the square of the linear predictor and the outcomes. And then the Hosmer-Lemmerschau test, there's no differences in the residuals relative to the deciles, the predicted values. And we can see visually that this is sort of following that zigzag pattern I was talking about, and that it's not really over predicting or under predicting the residuals based on what we're seeing here on this decile scale. So this kind of is a good guide for us to show that, yeah, this gamma log link model is not looking too bad when it comes to trying to predict the cost data in our data set. And just to compare all the different models so far, we see that the GL and log model is not too different from the OLS prediction. And we see that the mean, the median, and the mean are very similar. And since this had passed all of our specification and goodness fit test, this is actually probably a preferred model relative to, say, the OLS or the log OLS with smearing. So I'll put a check here as a model that you could potentially use. And before I move on, I wanted to check the chat. Jean, were there any questions from the audience? I heard some indicators, but I wasn't sure if there were questions for me.
Yeah, there was a question about the link test, and somebody wanted to know if it was the same as the Ramsey reset test.
Oh yeah, great question. So the Ramsey reset test is like omitted variable bias test, and it's not the same in the sense that we're looking at sort of the squared of the linear predictors to the actual data. What we're looking for with the Ramsey reset test is whether or not any of the independent variables should be powered, right? So in our model, I didn't square any of the terms, for example, but the Ramsey reset test would kind of tell you if it would be better to square some of the terms in the among your covariates. It doesn't tell you what's missing, right? It just tells you that, okay, something is a little bit off here, and maybe you can fix it if you try to add, like, say, some powers to some of the variables. At least that's how I've used the Ramsey test. I don't know, Jean, if you had any other interpretation of that.
No, I haven't used that test myself. But yeah, thank you for explaining that. Oh, and there was another question. You had talked about using the log OLS model, and somebody pointed out that you can't take log of 0. So I wonder if you have any recommendations for
so
the audience on what happens when you have 0 cost.
That's a very good insight. And in fact, that's very true. You can't get a log of 0 because you get an undefined term. And what ends up happening is that when you do this, a lot of those subjects end up becoming undefined. So you just have missing data there. And with Stata, at least my experience with Stata is that it still calculates some kind of predicted y hat, even though the log of 0 is undefined. But that's just the problem, right? Because those are technically missing data. And then this is why the retransformation is always an issue with the log OLS model. It's sort of a nasty business when it comes to doing it that way. But for years, people have just ignored that problem. I don't think there's a good way around it in the sense that you can't really do anything with that data set because it's just undefined. So for me, it's just not a good model to run. But yeah, that's a good comment.
Okay, great, thank you. That's it for the questions for now.
Yeah, great questions. And you can see quickly why, I just wanted to add why that log transformation is just a problem in general, right? It's just, one, it's hard to interpret what a log cost is, but more importantly, what if you had 0? And this is a problem when you have, as I mentioned earlier, with cost data, because you do have that point mass of subjects with 0 cost, and they end up becoming undefined. And when you look at them in a data set, they just become missing data. So it's always an issue. And I just don't think the log model is very good. But of course, there are some uses for it. I just won't get into that here. But when it comes to trying to estimate the mean, it's just not a very good model to run. But we do teach it in school because it's something that you'll see in some papers. So I'm going to switch gears a little bit and talk about the last model. And I think this is so we're kind of deviating away from the single equation model, right? Now we're looking at a 2-part model. And this is something that was designed in order to address that problem of that sort of large or significant point mass of subjects with 0 cost, because they tend to also skew the distribution. And as you recall from the original histogram that I'd written up, we do have a sort of a large point mass of subjects here that's near 0 or at 0. So how do we address those? The gamma model, the single equation gamma model that I showed you with the GLM structure, does a pretty good job of sort of getting it close to what the raw mean is. But it doesn't really answer the question, how does it deal with some of those zeros? So one way to deal with it, if you have a lot of zeros in your model or your data set, you can use a two-part model. And I think this is a kind of a cool model because you have the first part, which is a logit or probit model, which just asks the question, is your subject non-zero? So basically, do they have a non-zero cost associated with them? And then the second part about you can run anything you want. So here I just stuck with the traditional, or I stuck with my GLM model that fit the data really well the first time with a gamma distribution and a log link. And all you're really doing is just saying that, okay, if the you're getting the expected value of the cost data given some set of covariates X, and you're first checking to see what is the probability that the sample has non-zero cost. And then you're multiplying that with the expected value of Y, given that Y or the cost data is greater than zero. And then you're adding the probability of the subjects not having or having zero cost multiplied by the expected value of Y, the cost data, given that Y equals zero. And this is nice because you know this is zero, right? Because obviously if this is zero, this is going to be zero. So you just cross this out and that becomes zero. So all you're really focusing on is in this part of the equation. And then so we can run the logit model here, or the probit model here, and then we can run the GLM model here, and we can create the product. And that'll give us the conditional expected cost if the Y or the cost data is greater than zero. And this is really neat. I used to do this the old way where I had to do both models and then sort of do recycle predictions in order to get the 95% confidence bands. But I found out that the authors of the original paper for developing two-part models created their own Stata code. I believe there's an R code for this as well that does everything for you. So this is like a really nice innovation. So you can run this particular command with your traditional structural form of the model, and you can tell the first part of the model to be a logit model or a probit model. So I use logit here, and you can use the option for the second part to tell Stata what kind of model you're going to run. So in this case, we're going to run a GLM model with a gamma distribution, a log link. And you can predict the cost, right? Because when you actually multiply these terms, you're not really going to get the actual cost. You have to actually predict it, and you can summarize it. So here we have the mean cost, which is about $10,600, which is really close to the raw cost data. And we don't have any unusual like tails here. Everything is positive. And then our highest value is about $25,000. The skewness is 0.5, 0.47, which is closer to 0 than 0.6, which we got at the gamma model. My apologies, the GLM gamma model. And their kurtosis is around 3, which is what we would expect for a normally distributed data set. And as you can see, these are the predicted values from the two-part model, and it's much closer to what a normal distribution would look like rather than what you saw with the GLM gamma model. So everything's pointing towards the idea that two-part model might be a better model for this particular data set. And now let's go to our goodness of fit test, because I always like to do this to kind of confirm, or at least help me determine whether this model has any red flags. So there's no correlation between the residuals and predicted costs. That's a good thing, right? Because we don't want that to be significant. And then the link test here is telling us that the model specification is appropriate, that it's not deviating too much, because you don't want these squared predictors to sort of explain any of the outcomes, right? They should all be explained in the first part of the linear predictors. And then the Hosmer-Lemaitre test is also non-significant, seeing that the mean residuals are no different from 0 across the different deciles. And I also like to plot this just to kind of show that we're getting that nice zigzag pattern here. We're not really seeing any overestimation or over-prediction or under-prediction of the residuals across the fitted deciles. So this is actually looking pretty good. Now we can compare all the models now, and just looking at the different just values for the mean, we see that the OLS is clearly a very good predictor of the raw data. But then you can also see that the GLM model with log link, as well as the two-part model using the gamma distribution of log link, also do a pretty good job of predicting the raw data. But what I also want to demonstrate is that, oops, before I move on to the next poll, I don't have this here, but we also saw that the kurtosis and the skewness was pretty close to 0 and 3, which is what we would expect from a normal distribution. Just kind of nice way to sort of summarize all the models we talked about today, and also how different they are in terms of their mean, their median, and also their min and max. And then I guess this is the last poll question, Maria. So just want to ask the audience, after seeing all of this now, which model would they like? Would they use in the future for their outcome if it was a cost data set?
Okay, hold on one second, and let's see. Trying to get that poll to open. It's giving me a little bit issues. Hold on one second. Okay, here we go. The third poll is now open. What model would you use for cost as an outcome? A, ordinary least squares linear regression model. B, the log transformed log OLS model. C, generalized linear model. Or D, the two-part model. And the responses are coming in, and it's slowed down, so I'm going to go ahead and close that poll. And the results are 2% say A, 6% responded B, 35% responded C, and 54% responded D. And back to you.
Great. Yeah, I think that's a really nice sort of distribution of answers. I also think that the ordinary least squared model is also a very good model in the sense that it's not very complicated to run. You get a pretty good estimation of the mean, and it's very easy to interpret, right? But again, if your concern is about specification, then it probably wouldn't fit the data very well. And but I do think there could be a tie between the GLM model and the two-part model, depending on how complex you want it to be, and also whether or not you have a lot of zeros in your data set. So this is just a nice summary of the modified Hosmer-Lemmerschau test, kind of show you visually how different these models are. I took away the log OLS model just because it just overpredicted the residuals way too much to fit into here. So I only picked the 5 models that I looked at, or the 4 models I looked at that are pretty close to the 0 residual. As you can see, the smearing model really doesn't do a good job here with the residuals, but OLS, GLM, and also the two-part model are not too bad, just visually when you look at this. And this kind of is a sort of a lesson that, you know, sometimes simple models can be useful if you just want to get a simple answer. But if specification was really your goal, then you can go with either the GLM model or the two-part model, because they do pass all the specification tests and also the correlation tests we're looking for. So I think between the GLM and the two-part model, this would be a tie for me. But if I was looking for something quick and easy to do, the OLS model would still give me that answer. So just kind of want to let you know, these are just guideposts to help you determine what kind of model you can run when it comes to cost as a dependent variable. And also determines what the editor wants when you publish papers, because sometimes they prefer to see like more specification testing or goodness of fit test to make sure that you're doing it correctly. And that's generally what I do. I always try to provide the goodness of fit test in the appendix or as part of the discussion in my paper to kind of let them know that I did my due diligence and check to make sure these models are fitting the data correctly or appropriately. That's kind of something that I always do. And hopefully the GitHub code that I provided will help you do that also. All right. And I kind of want to reiterate that I did put all the data and the data code in GitHub, so you can click on this link here and download that. And I also have some papers here that are sort of seminal papers in the area of using cost as a dependent variable. And Will Manning did a lot of work in this area. One thing I wanted to point out is there are other models out there that you could also use, but I haven't gone through them yet. One, because they're a little bit more complex to discuss, and also there's some limitations with them. So for example, there's the EEE model, which is the extended estimating equations model, which is more of a very empirically run model for the GLM, which helps you select the correct family and link. But you need to have a lot of data in order for that to work. Otherwise, you have some convergence issues, and also some finite models you can run as well. But I think when it comes to publications and what I see, I generally see a lot of the GLM gamma model and two-part models in the literature. at least for now. I am seeing more of the EEE models being published, but again, like I said earlier, you need to have a lot of data for that in order for it to converge. And just as a reminder, Paul Barnett did a really wonderful job of this sort of series where he talked about the cost as a dependent variable in terms of a theoretical foundation, as well as some practical uses of the different models that are available. And I think most of his work has been using SAS. So if you're interested in looking at some of the SAS code, Paul has provided that in these presentations. Okay. And then one acknowledgement, I have a lot of acknowledgements to make, but the one I really wanted to at least point out is that a lot of the stuff I've learned with cost data really came from the courses I have attended at the University of Washington Advanced Method course series. And I drew a lot of inspiration codes from the lectures from those materials. And I still use them to this day because they really have stood the test of time. So hopefully they're helpful for you in your own research and work. All right. And hopefully I left enough time for any questions or comments or feedback.
Yes, there's a few questions here for you, Mark. So one question asks, can you use the two-part model command and include post-estimation correction for error clustering?
I believe you can. So just to clarify, are they asking about the robust standard errors?
Do they talk about error clustering?
Oh, like cluster on different like longitudinal data sets, hierarchical models.
Yeah, I think that's what they're referring to.
Yeah, I've had success using that, and I've had success using two-part model with complex survey designs where you do have clusterings there. So yeah, my experience is yes, that you can do that.
Okay, great. The next question asks, or actually I guess it's a statement, two-part models make more sense with fairly rare events like ER visits, but oftentimes that often do not fit Poisson very well because there are folks who are serial ER users. And then with costs, you have to choose some cutoff for what's effectively zero. Some people may have $5 or $20 worth of healthcare costs in a year. So should you count those as zero or not in the first part of the model?
Yes. So the first part of that statement, the two-part model, because you can use a gamma, a GLM model in the second part, you can also get count data too. So it's very useful in the sense that it's still flexible to do both count data as well as cost data. And of course, if the Poisson doesn't work, you could always try a negative binomial model. In regards to how to categorize zero, I guess that's really dependent on the investigators in terms of how the cost is spread and dispersed. I generally don't categorize, like say something that's low cost at like $5 as zero. I like to keep the original raw data because those are still meaningful to me, at least when I start investigating that. So I don't generally collapse that. But when you do collapse, you're also losing you're sort of losing the data, right? Because that's still rich data. And when you start collapsing things, you tend to lose some of that sort of specificity of that, or the richness of that data. But again, it depends on what it is your research question is. If it's more important to look at sort of categories of costs being spent, then maybe it's useful to collapse them. But I also think you are sort of not using the full potential of that data set by doing so.
Yeah, I would agree with you there. There's a difference between having zero costs and having some costs, even if the $5 is, some sort of low cost drug that you're taking. So there are reasons not to, consider low cost as zero. And I think that's pretty standard. Okay, so the next question asks, other than the log model, how are the coefficients similar between the two-part models and GLM and OLS?
So for the OLS model, the coefficients are just easier to interpret. It's still on the raw scale, right? So whenever you see a coefficient for an OLS model, you can interpret it as sort of the change in cost due to a 1 unit change in the independent variable, the covariate you're looking at. With the GLM model, when you do, like say, I think if you do predict, when you do the predict command, you have to specify that you want to make sure your using the log of the expected cost given the array of covariates. Otherwise, it's going to give you sort of a log interpretation of the GLM results. So always make sure that when you do the predict command for stata that you use the mu option, which gives you the transformation. Similarly, with the two-part model, it's nice that Bilotti and Will Manning, and Deb were able to create a stata command because it does it for you automatically. But when I used to do it, I had to actually create the product term and then transform it myself at the end, and then do some additional transformations in order to get the actual cost data. So because when you look at the logit model, right, it's giving you a probability, and then you're looking at the GLM model, which is all giving you some kind of coefficient in the long term. So combining them becomes a challenge when you try to do it manually. But at least the two-part model, when you're doing it, make sure you use the predict command with the mu option, and it'll give you the cost data in terms of its in the form that you want to interpret it as. So those are the differences when it comes to the beta coefficient, those models. I don't know if you had any insight, Gene, on some of those coefficients.
No, I think that you explained that really well. Thank you. Yeah, so I don't have anything else to add to that. The next question asks, can the two-part model offer more understanding of the underlying process across users and non-users of healthcare compared with the GLM model?
Yeah, that's a really great question. And I think when it comes to the two-part model, whenever I use it, I take advantage of the two parts. So you have that first part, which is the logit or probit part, which tells you the probability that the sample you have non-zero cost. So that's information that's useful, and it could be useful for a stakeholder. The GLM single equation model won't tell you that. It just tells you on average what is the sort of cost, right? So at least the two-part model gives you that first part, which is really unique from other models that I worked with. And again, you have the ability to condition the average cost, whether or not you actually have non-zero cost, which makes sense to me when you think of the sort of population trying to study.
Right. You can have a different process for whether or not a person had any healthcare costs versus non-healthcare costs. Mm-hmm. And that process may be different than once you have healthcare costs, do you have higher or lower healthcare costs? And so that's the advantage of the two-part model.
Yeah, absolutely.
So somebody asked, I think a question we're all wondering is that, have you been able to persuade journal editors to accept OLS for costs?
Maybe 30 years ago, but today I think editors and reviewers, right, are more sophisticated when it comes to recognizing some of the limitations of using OLS to predict cost data and even count data. I think if you're just looking for just a simple answer, you're not too worried about model sophistication, you can get away with that. But I do think as sort of health services researchers, we should provide some level of insurance, right, that the model is actually correctly modeling the data that we have in front of us. So I don't know if we can still persuade journal editors or peer reviewers that OLS is better. It's informative. I don't know if it's better than, say, a GLM or two-part models or any other more sophisticated model that does fit the data better, because you really have to define what does better mean, right? Does better mean fitting the data better, or does better mean getting an answer more quickly? I guess it really just depends on the interpretation of that.
Yeah, great. And I should say that I actually have published some papers using OLS for costs. And that was because we had various outcomes. And also, when you do OLS in a paper, you generally do sensitivity analyses where you might be testing other types of models, like, log OLS, mm-hmm. log transformed models. So it is possible that, as you suggest, viewers will often want you to use a more rigorous type of model.
Yeah, I'm glad you brought that up, Jane, because I remember when I was in school and we were learning this, people were in class were like, why even use the OLS model? And I remember a professor saying that because it's so easy to interpret. It's not complex at all. And if you're just looking for just the mean or just on the average, then that's a good model to use. So why make things more difficult for people when they're trying to make decisions?
Right, right. And of course, a lot of reviewers understand OLS better than other more complicated models.
And as I demonstrated, the OLS is pretty robust, even to violations of normality. So it's not that you throw the model away. It's still a decent model to use.
Mm-hmm. Mm-hmm. Yeah, definitely. Okay. There's another question that asks, can you talk about the distinction between hurdle models and two-part models?
Yeah, to be honest, I don't really have a lot of experience with hurdle models. I think my interpretation is that it's very similar in the sense you are sort of breaking things up, but I don't really use hurdle models. At least I don't use that term when describing the models I use. I don't know, Jean, do you have any experience using hurdle models or applying them in your work?
I've had collaborators use hurdle models, and I know they are a little bit different from two-part models, but I don't know enough to say much about it. If you are interested in learning more about it, you could email one of us, and we could probably send you some references. So
It might even be an interesting future cyber seminar. We can probably try to find some experts to talk about that.
yeah. So if you are interested in that, then feel free to let us know in the post-seminar survey that goes out, because we definitely want to know what topics people are interested in. Okay, I think that was the bulk of the questions. So thank you very much, Mark, for the wonderful lecture. Maria, do you want to say any last words?
Sure. Mark, do you want to go ahead and put on that last slide about how to contact you?
Oh, yeah. Let me just see if I can move that over. Here we are.
So if you have any questions or suggestions, you can reach out to HERC. Also, I want to apologize. The slide link for today's handouts has been corrected. So if you could see in the chat, there's a place for you to copy and paste that. It's also in your reminder email. So and if for some reason you're picking up the old presentation, just clear your cache and or try a different browser. But thank you so much, Mark, for presenting today, and thank you, Jean, for moderating the Q&A. Join us for April 28th for our next HERC session.